According to the theory of evolution, the origin and development of the universe and all its systems can be explained solely on the basis of time, chance, and continuing processes. All living things have arisen from a single-celled organism. A second and opposing worldview is the concept of creation. According to the theory of creation, everything in the universe has come into being through the design, purpose, and deliberate acts of a supernatural creator. That means this creator created the universe, the earth, and all life on earth, including all types of plants and animals, as well as humans. On today's edition of Origins, we'll discuss the largest organ in the body, our skin.
Hello, my friends, and welcome to Origins. My name is Donn Chapman, and it's my privilege to be your host. Origins is a forum where we take the evidence of science and we use it to validate the truth of creation. We have a great guest for you today. His name is Dr. David Menton. Dr. Menton, for 34 years, taught in the medical school at Washington University in St. Louis, Missouri. Dr. Menton, it's a high privilege to have you with us today.
Oh, my pleasure, Don.
We're thrilled that you're here. Now, we're always hearing this line that we have up here as the intro, that beauty is skin deep. I guess I want to ask you, how deep is that?
Well, it depends on where you're looking. On the foot pads and on the palms, it's quite thick. On our foot pads, it's 3-4 millimeters thick, which if you think of a dime as being a millimeter, 3-4 dimes stacked, you know, pretty thick with the dermis and everything. Thinnest skin on our bodies, on our eyelids, right here, just over the eye. It's like a sheet of tissue paper in thickness. One way to study skin is just to jump right in and look at skin. Here's a young lady. In fact, you may be interested to know, Don, that this is actually one of my former medical students listening to me give a lecture.
Is that right?
Right. When we look at skin like that, we really can't see too much about it. We can't see how it works. It just kind of looks homogeneous, so we might want to magnify it a little bit. So let's really crank up the power here. Oh, now I think that's a beautiful lady right now. What do you think, Don?
I like the first picture better.
You have to be an anatomist to appreciate this. But you know, anatomy means to cut to pieces.
Oh, is that what it means?
That's what the word means. And so I think we need to look inside the skin. And to do that, we'll make a little incision. And if you don't mind, I'll just get up and...
If you're making incisions, I guess that gets to be gross anatomy. Okay, but you go up to the screen and show us what you got for us, my friend.
When we magnify the skin at this level, then we can see that it has little folds and crevices in it that allow it to kind of stretch. There are places right here where you can see there's a little tiny hair that's growing out there. We'll have a separate lecture someday on hair. But these little folds and crevices are all over the surface of the skin. And what we need to do is to make an incision right there. If you can't stand the sight of blood down, you might want to look the other way, because here goes the cut. Right in. This is a cross section. And in this cross section, up here at the top is the dead layer of the skin, the stratum corneum, the surface of our body. Below that, this dark layer that you see right here, that is the living epidermis. And from that level all the way down, that's called the dermis. That would be like the leather. If you look at the leather of a wallet, that's the dermis of a cow.
Okay.
Now, we can magnify. Let's begin magnifying the dermis itself. We take an area such as you see in the box there, actually a little smaller, and we blow that up and look at that in the scanning electron microscope, and it's sort of like looking at a straw pile. The interesting thing here is that those fibers just aren't willy-nilly. They are woven. So, and then in between these fibers, there is liquid. And this liquid is not like water. If it were, we'd gurgle when we walked. It's more like a gel.
Okay.
Now we're going to really crank up the power. This is a scanning electron microscope that looks in 3D. And to see the weave that we have here, let's go up a little higher power yet and look in a transmission electron microscope. And notice here that the little tiny fibers that make up the dermis, the connective tissue of the skin, here they are coming at you. So you just see dots, because all those fibers are coming at you. Up here they're going crossways. So you see them like that. Here they're going crossways. Some places they're going kind of at an angle over here. And this whole thing is just woven. In fact, our body is woven together, all of the organ capsules, the dermis, and what have you. And this weave is something we really haven't begun to really understand. Our skin is stretchy, isn't it? When you're younger, it's even more stretchy than when you get older. But to be stretchy, remember, the fibers that make up the dermis, which is most of the thickness of the skin, are less elastic than steel.
Really?
And are considerably stronger than steel.
Stronger than steel.
And less elastic, and yet that's what makes stretchy skin. Now, how is it possible for something to stretch and still be made? It's like being made out of chainmail, except we're stretchy.
You're going to have to explain that to us.
It's the weaving. You know, the Bible says that the Lord weaves us together in our mother's womb. It uses that, knits and weaves, and here we can see it. And the weaving is complex beyond anything we can imagine. Let's just take a peek at that. Various laboratories, particularly in the leather industry, have tried to do some weaving to see just what kind of a weave pattern would account for what we see in the skin, and nobody's quite been able to come up with it. You think of a double knit fabric in these elastic suits and what have you. That requires a certain weave to produce that stretchiness, whereas it's a different weave in a web belt or in a conveyor belt that has no stretch at all. And so some areas of our body, the weave is designed not to stretch. In other areas, it's designed to stretch. Some years ago, a German scientist, many years ago actually, took a deceased individual, a cadaver if you will, and punched holes all over in the body. And he noticed that when he punched the hole with something like an ice pick, when he took the pick out, the hole wasn't a round hole, it became a slit. And you could sort of take the long axis of these slits and draw lines, and you notice that the lines follow particular patterns on the body. These are called Longer's lines. Plastic surgeons take advantage of that. And so that represents sort of the warp and woof of the fabric of our body. Well, here it is, Psalm 139. For you formed my inward parts, you wove me in my mother's womb. I will give thanks to you, for I am fearfully and wonderfully made. Wonderful are your works, and my soul knows it very well. I always think that it might read, wonderful are your works, and that's like a no-brainer.
Yeah.
There's two kinds of skin in our body. There's thin skin and thick skin. Most of it is thin. That's what you have on your trunk of your body, on your arms. The thick skin is just on the palms and the soles, and is designed to resist the wear and tear that those surfaces get. Here we can see thin skin. It has thin epidermis. It's been sort of peeled off like might happen in a blister, and the dermis is pretty thin as well. Over here in thick skin, like from the soles or the palms, the epidermis is thick, and the dermis is also very, very thick, and the junction between the two is very folded. That kind of makes it resistant to being peeled off or sheared off. This is the way it looks in the flesh. If we make a section through the fingertip, you can see the fingerprints here. See the little ridges? That's where the ink goes for a fingerprint. And the dermo-epidermal junction's kind of folded. If you look at this from above, in the scanning, or in the light microscope actually, you can see these ridges, and they are the fingerprints.
Yes.
And can you see the little tiny dots every so far along here? That's where the sweat glands come through to the surface. And only water can soften this dead layer. lanolin, oil, things like that cannot soften the dead layer of the skin. Only water does this. What oil does is to make a film over the top that keeps the natural water of the body in, and so the softening is our water.
So the oil isn't, when I put a hand cream on, it's not really penetrating, it's just allowing it to retain the water that's already in there.
Probably not penetrating much, right? It's
Yes.
retaining the water, and it's the water of your body that's softening that stratum corneum. Once again, we sort of have to leave things up to the Lord.
Yes, we do.
That folded dermoepidermal junction, say in our fingertips, is one that we have to feel things through, and yet the epidermis is so thick. How do we feel anything through that thick layer? We have special nerves that go up into these little pockets underneath the epidermis that are sensitive to touch. And these little nerve corpuscles allow us to feel ever so fine of texture.
So that even though our fingers are part of the hand where the skin is the thickest, we still have sensitivity there.
That's the most sensitive part of our skin. You know, if you take two pins and put the pins against your abdomen or back, it's hard to tell whether they're 2 pins or 1 pin until they get about an inch or so apart. But on your fingertips, think of somebody who can feel Braille.
Yes.
Those pins could be very close together, and that's thanks to these very special nerve endings.
Amazing.
That are located there. Another thing we see in skin is that there are many capillary loops. These are these tiny little blood vessels that come up and down like this just below the surface. They are involved in controlling blood pressure because there's little automatic valves down here that turn on and off and run the blood to the surface or deep. That makes us look red or pink or white, if we're Caucasian at least. And so they play a role in controlling blood pressure, but most importantly, they play a role in thermal regulation. This is how we lose heat from our body. Heat can be lost from the surface of the skin by causing this blood to flow up near the surface. Well, there's many things we could say about this, but let's just look at the whole pattern of how those cells in our epidermis develop. They start in the bottom, in this lowest layer, and this is where they divide to make 2 cells. And other cells are dividing. And they move up in the epidermis, and as they move up, they fill up with a special protein called keratin, which is very tough. That's the sulfur smell you get when you burn skin or hair or fingernails. It's a cross-linked with sulfur, and it makes a very strong protein. And at some point up here, all of a sudden, the cell dies. This is programmed cell death. This isn't just by chance. It just gets turned off. And all the rest of the epidermis then consists of dead cells stacked one on top of another. And it's that layer of dead cells that is the barrier that keeps our body from losing water and put us into shock and die. In fact, if all you did to somebody was to simply remove the dead layer, you just take it all off, they'd probably die within an hour.
So all of the skin that you can see on a person is dead.
Everything on the surface is
Everything
dead.
that you see is dead skin.
Many layers thick, all dead.
Huh.
And it needs to be dead to serve its function, which is to be a barrier to water so that it doesn't leak out of our body. By the way, to go from the bottom up to the top, where the cell finally just falls off, one at a time, all over our body, one at a time, just keep falling off, is 28 days.
That's all it takes. In
about
less than a month, it's all gone.
Each month, we're completely turning over the whole surface layer of our body.
I'm a new man every month on the outside.
Absolutely. Every month, completely
amazing.
new, which if you think about it, our skin doesn't get any older then, does it? Although it does change with time.
It's amazing.
Let's look at what these cells in the epidermis might look like as they're filling up with keratin. They become quite large. Look how big this cell is here. It's nice and big and round. This is the nucleus in here that has all the genetic material. The keratin is all over out in this area. And the thing that's interesting is if you look really carefully, right between these 2 lines, let's say here, you can see what looks like a zipper in here.
Yeah.
And this is where one cell of the epidermis is locked into another. It's rather like buttons here on the coat. There are about 200 of these buttons per cell that button it to every other cell so that they don't come apart. They're buttoned together. In addition to that, there's a special glue in there, an adhesive that holds it together. And yet, these buttons and that adhesive has to release at just the right time so that the cells can fall off the surface every 28 days to get to the top, each cell layer is going to fall off. If it didn't, we'd get thicker and thicker. And
So,
if they fell off 1% too quickly, it would take no time at all. You wouldn't have a dead layer, and you'd be dead.
1%, it has that kind of, it's
Right.
that precise.
If it were 1%
If it
falling
fell
off faster than
yeah.
they were being produced, then within a matter of
die.
months, you would have no stratum corneum, and that would be fatal.
Isn't that amazing?
So
And yet, if it was made to adhere longer, we would just get so thick
it looked like
that
an
we
alligator.
couldn't
just
move. Yeah.
thicker and thicker.
That's
See,
amazing.
this is what the dead layer looks like. We have come up to the surface here, and this cell right here is a dead cell, whereas the cell below it down here is a living cell.
Okay.
And so we go from living to dead, just bang. Something just shuts off the life of this cell. Here's the nucleus just breaking down. You can see there's just a kind of a flat little structure. And then up here we see no more
No
nuclei
nucleus at
anymore. And these dead cells are all attached to one another by little interlocking mechanisms that hold them together. And this forms a barrier to water loss. And without this barrier, as I say, we die probably within an hour just from shock, from loss of water. Serious burn patients, this is a problem, losing the surface.
We got to take a break right now, but don't you go away, and don't you go away, because we're going to come back and there's still a lot more for us to learn. And I want you to share in this great knowledge about our creation, the human body, and about our great Creator. So we'll be back in a minute.
Creation versus evolution. You weigh the evidence. Man's framework, an engineering marvel. The 206 bones in the human skeletal system are an engineering marvel. It is a rigid support for the body's organs and tissues, serving as a shield for the brain, lungs, heart, and spinal cord. Engineers are developing lightweight structural materials, but have yet to devise a substance that grows constantly, lubricates itself, requires no shutdown time, and repairs itself routinely. Is man's framework a product of random chance processes or the creation of a grand designer?
Today's guest on Origins, anatomist Dr. David Menton, is a speaker for Answers in Genesis. Audiences enjoy his well-illustrated presentations on a variety of fascinating topics. Many of these lectures are available on DVD. If you're interested in the subject of creation, you'll definitely want these for your own. Orders are being taken at 800-778-3390. You can also write to Answers in Genesis, P.O. Box 510, Hebron, Kentucky, 41048. Or visit the website at www.answersingenesis.org.
Welcome back to Origins. I'm here with Dr. David Menton, and we're talking about skin and how intricately God has made our skin. Dr. Menton, we talk about thick skin and thin skin. I used to think thin skin's what my parishioners had and thick skin's what I had, but we all have some thick skin and some thin skin. Is that right?
Yes, they serve two different functions. For example, this is a cross-section through just the epidermis of our thick skin that you would have on your foot pad or on your fingers. And the dead layer is really thick in thick skin. The function of thick skin is a barrier, wear and tear barrier. Those cells are made to not tear apart or let go. Those little buttons in the adhesive we talked about.
There's more buttons and more glue in there.
Work well, a better glue. This is the living layer down here, and when these cells divide and get up to here, they form the dead layer. Some years ago, what I did was to take a piece of adhesive tape, put it on the bottom of my foot, and tear it off, and that pulled some cells off. You know, if you work with sellotape, you leave your fingerprints on the tape.
Sure.
Well, those fingerprints are the dead cells you pulled off with the tape.
Okay.
If you put the tape in the scanning electron microscope and look at it, this is what one of those cells looks like.
So that's actually a picture of your foot.
This is a picture of one dead cell.
From your foot.
You know, one of these little things up in here.
Wow.
Viewed from the surface, and notice how folded the surface is. And what that does is it produces an interlocking mechanism, sort of tongue and groove interlocking mechanism, which keeps one cell from being sheared off the other.
They're holding each other in place.
Right. The interesting thing is, although this skin is thick, it's not a particularly good barrier to water loss. It's fairly leaky. Water can get through here much easier than it can on skin from the rest of our body. Let's take a look at thin skin. This is a cross-section of thin skin. Notice how relatively thin the stratum corneum is. Some of it's been lost in the preparation here. And the living layer is also thin, and the dermis is somewhat thinner too. You wouldn't think that would be as good a water barrier, but this is the best water barrier. So it has less resistance to wear and tear, better for water. Now, some years ago, I took a piece of sellotape and put it on my tummy and pulled it off. And this is one of the dead cells that was on the surface. This down here, by the way, is the adhesive of the sellotape. And look, this looks like a saran wrap floating on water. Very, very thin, incredibly thin cell, but very broad. And it's a stack of these very thin cells that produces the barrier to water loss that allows us to survive in our
It looks very
atmosphere.
different. It doesn't have all those little things, and so there's less place for the water to go through.
That's right. It doesn't have the resistance to shearing because they're flat, but because of the way this cell is made, its resistance to water loss.
That's amazing.
Some years ago, I did an interesting experiment where I made a cross-section through skin of actually ear epidermis from a mouse. You can see the dead layer up here. This is the dead layer of the mouse ear here. And if we take this section and we soak it in a substance that dissolves keratin, a really remarkable thing happens. It swells up.
Look at that.
And when it swells, we observe something I guess we would have never guessed. And that is that the cells of the epidermis, those dead cells, are stacked just like poker chips in a casino, I've been told. The stacks interleave at their edges. So as we go down the line here, we're getting an absolutely perfect interleaving. In other words, one column here, one column here. Perfect. You never see a miss. It's a perfect interleaving. If we magnify an area like that and look at it at the transmission electron microscope, here we can see this perfect interleaving right on down the line at high magnification here.
Isn't that amazing?
Of these cells. And you know what's really intriguing is if we magnify this, let's take that one dead cell, blow it up in the transmission electron microscope, what do we find? We're back to weaving.
Yes.
Inside these dead corneocytes, we find filaments running this way. We find them running this way that are coming at you, others going at an angle. The keratin is woven. We even have weaving inside of each of the dead cells. And you want to see something really fascinating? See this little structure right here? That's one of those buttons I was telling you about. We call them desmosomes. About 200 buttons per epidermal cell holding them one to another. Here's one still hanging on in the dead layer. And this button, together with the adhesive that's formed between the cells, must be released so that cell can fall off at a rate that precisely matches the production of cells at the bottom of the epidermis. And when I see that, I know there's a crater. By the way, I should conclude by telling you that when you study just exactly how these columns of cells are arranged, in their rows like this, if you look down from the top, they look like hexagons. It turns out that each one of these cells is a particular shape. It's a polygon, known as a tetrachedecahedron, a 14-sided figure, and each cell achieves that shape to be able to form these columns.
It's amazing. Come down here and join me, my friend. I'm just fascinated by the skin. The outer layer is dead, but it's an organ. The skin is an organ, but it holds my body together and holds the water in. Even when it's dead, it's a functioning organ. Is that right?
Yes, it wouldn't be functional if it were alive.
Isn't that amazing?
In fact, this is one of the problems in psoriasis. The layer does not die and form a proper dead cell. It still retains some incompletely dead cells, and the skin leaks water. And here's a case where our ability to survive in the environment that we live in, even to survive for 1 hour, requires this exotic structure we've just discussed, requires this careful control of cell turnover, requires this special glue, these special buttons, this special keratin, with this marvelous resistance to being penetrated by water except in small quantities. And to me, that is just the handiwork of a designer and creator.
You know, you used that word special several times. You're a special gift to the church
Oh, thank
for
you.
us to be able to see these things that we wouldn't know. You know, it's God's view that He created you, and that should be your worldview too. So until next time, I hope you'll appreciate the greatness of our Creator. God bless you.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 710 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins, program number 710, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.